a corner-grounded delta system, it's true that the grounded line is theoretically at zero potential to ground, even with current flow. The grounding's purpose is to create a low-resistance path for fault current to return to the source. During a fault, current flows through the grounded line, bypassing other lines and the load. This keeps the grounded line at ground potential, seemingly safe. However, this safety is theoretical. In reality, a small voltage drop can occur on the grounded line due to the ground connection's resistance. This drop, though small, can cause a shock. Because of this possibility, touching any electrical line, even a grounded one, is discouraged. When working on a corner-grounded delta system, safety measures are crucial. This includes using rubber gloves and insulated tools. A corner-grounded delta system is a type of three-phase electrical power system. In a delta system, the three phases are connected in a closed loop, forming a triangle. The corner-grounded aspect means that one of the phase conductors, specifically at a corner of the delta configuration, is intentionally connected to ground. This connection to ground serves several important functions. Firstly, it provides a reference point for voltage measurements within the system. Secondly, it helps to limit the voltage to ground of the ungrounded phases. Thirdly, and perhaps most importantly, it provides a path for fault current to flow back to the source in the event of a ground fault. In a corner-grounded delta system, the voltage between any two of the ungrounded phase conductors is the delta voltage, which is the highest voltage present in the system. The voltage from either of the ungrounded phase conductors to ground is the same as the delta voltage. The grounded phase conductor, as the name suggests, is at or very near 0 volts relative to ground. Now, the safety aspect of touching the grounded conductor. Theoretically, because the grounded conductor is at zero potential relative to ground, touching it should not result in an electrical shock. This is because there is no voltage difference between the conductor and the ground, and therefore no driving force for current to flow through a person touching it. However, this is a highly idealized scenario. In practice, several factors can compromise this theoretical safety. Firstly, the ground connection itself may not be perfect. There will inevitably be some resistance in the grounding conductor and the connection to the earth. This resistance, even if small, can result in a voltage drop along the grounding conductor when current is flowing through it. This means that the grounded conductor may not be exactly at 0 volts at all points in the system. Secondly, there may be circulating currents in the grounding system due to ground loops or other imbalances in the system. These circulating currents can also cause voltage drops along the grounding conductors, further raising the potential of the grounded conductor relative to ground. Thirdly, and perhaps most importantly, the system may not be operating under ideal conditions. If there is a ground fault somewhere else in the system, the grounded conductor will be carrying a significant amount of fault current. This fault current will cause a substantial voltage drop along the grounding conductor, potentially raising its potential to a dangerous level. Furthermore, even if the grounded conductor is nominally at 0 volts, there is always the risk of induced voltages from nearby conductors. Electrical conductors carrying current produce electromagnetic fields, and these fields can induce voltages in nearby conductors, including the grounded conductor. These induced voltages may be small, but they can still be perceptible or even dangerous under certain conditions. Given these factors, it is never safe to assume that the grounded conductor in a corner-grounded delta system is completely free of voltage. Touching any electrical conductor, regardless of its intended potential, should always be approached with extreme caution. Appropriate personal protective equipment, such as rubber gloves and insulated tools, should always be used when working on or near electrical equipment. Additionally, it is important to verify the absence of voltage on any conductor before touching it, using a properly rated and calibrated voltage tester. Furthermore, the National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems to ensure safety. Some of the relevant articles include Article 250, which covers grounding and bonding, and Article 450, which covers transformers, including those used in corner-grounded delta systems. These articles specify the required size and type of grounding conductors, as well as the methods for connecting them to the earth. Adhering to these requirements is essential for ensuring the safety of electrical systems. In summary, while the grounded conductor in a corner-grounded delta system is theoretically at zero potential relative to ground, this is a highly idealized scenario. In practice, several factors can compromise this safety, including resistance in the grounding conductor, circulating currents, ground faults, and induced voltages. Therefore, it is never safe to assume that the grounded conductor is completely free of voltage, and appropriate safety precautions should always be taken when working on or near electrical equipment. Let's delve a little deeper into the practical considerations and safety precautions. Firstly, always assume that any conductor is energized until proven otherwise. Use a properly rated and calibrated voltage tester to verify the absence of voltage before touching any conductor. Secondly, wear appropriate personal protective equipment, or PPE, including rubber gloves and insulated tools. Rubber gloves should be rated for the voltage level of the system being worked on, and they should be inspected for damage before each use. Insulated tools should also be rated for the voltage level of the system, and they should be free of any cracks or other defects. Thirdly, work in a dry environment whenever possible. Water is a good conductor of electricity, so working in a wet environment increases the risk of electric shock. Fourthly, use a buddy system. Have someone else present who can assist in case of an emergency. Fifthly, energize the circuit before working on it whenever possible. This is the safest way to prevent electric shock. If it is not possible to de-energize the circuit, use appropriate safe work practices, such as keeping one hand in your pocket and using insulated barriers to protect yourself from accidental contact with energized conductors. Sixthly, be aware of the potential for arc flash. Arc flash is a dangerous phenomenon that can occur when a short circuit occurs in an electrical system. Arc flash can produce intense heat, light, and pressure, which can cause serious burns, blindness, and even death. Wear appropriate arc-rated clothing and PPE when working on or near energized electrical equipment. Seventhly, follow all applicable safety regulations and standards. The NEC and other standards provide detailed requirements for working on electrical systems safely. Be sure to familiarize yourself with these requirements and follow them carefully. Eighthly, get training. Electrical work is dangerous and should only be performed by qualified personnel who have received appropriate training. If you are not qualified to perform electrical work, do not attempt to do it yourself. Ninthly, understand the specific characteristics of corner-grounded delta systems. These systems have some unique characteristics that can affect safety. For example, the voltage to ground on the ungrounded phases is higher than in other types of systems, so it is important to use appropriately rated PPE. Tenthly, maintain the grounding system properly. The grounding system is a critical safety feature of any electrical system, and it is important to maintain it properly. Inspect the grounding conductors and connections regularly to ensure that they are in good condition. Replace any damaged or corroded components. Ensure that the grounding system is properly bonded to all metal enclosures and equipment. In addition to these general safety precautions, there are some specific considerations for corner-grounded delta systems. Because one phase is grounded, a ground fault on either of the other two phases will result in a line-to-ground fault current that is relatively high. This high fault current can cause significant damage to equipment and can also be a safety hazard. Therefore, it is important to use overcurrent protection devices that are properly sized and coordinated to protect the system from ground faults. Also, because the voltage to ground in the ungrounded phases is higher than in other types of systems, it is important to use insulation that is rated for the appropriate voltage level. Using insulation that is not properly rated can lead to insulation failure and electric shock. In conclusion, while the grounded conductor in a corner-grounded delta system is theoretically at zero potential, it is never safe to assume that it is completely free of voltage. Always take appropriate safety precautions when working on or near electrical equipment, including wearing appropriate PPE, using insulated tools, and verifying the absence of voltage before touching any conductor. Remember to work safely and follow all applicable safety regulations and standards. The electrical safety is everyone's responsibility, and by following these precautions, you can help to prevent accidents and injuries. The corner-grounded delta configuration presents distinct characteristics compared to other three-phase systems, particularly in scenarios involving ground faults. In this system, a ground fault on one of the ungrounded phases directly translates to a phase-to-ground fault, triggering a substantial fault current. The magnitude of this fault current hinges on factors such as the system's impedance and the grounding conductor's resistance. This high fault current presents heightened risks, including equipment damage and potential electric shock hazards. Effective overcurrent protection becomes paramount in mitigating these risks. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a predetermined threshold. In a corner-grounded delta system, these devices must be carefully selected and coordinated to respond swiftly and effectively to ground faults. Proper coordination ensures that the device closest to the fault location clears the fault, minimizing disruption to the rest of the system. Furthermore, the voltage to ground levels in a corner-grounded delta system differ from those in other three-phase configurations. Specifically, the voltage to ground in the ungrounded phases is higher. This elevated voltage to ground necessitates the use of insulation materials with appropriate voltage ratings. Insulation failure can occur if the insulation is not adequately rated for the voltage levels present, leading to potential electric shock hazards and equipment damage. Therefore, meticulous attention to insulation ratings is essential in ensuring the safe and reliable operation of corner-grounded delta systems. In summary, the corner-grounded delta system introduces unique considerations for electrical safety, particularly concerning ground faults and voltage-to-ground levels. Robust overcurrent protection schemes and appropriately rated insulation materials are critical components in mitigating the associated risks and ensuring the safe and reliable performance of these systems. It's also worth noting the importance of regular maintenance and inspection of corner-grounded delta systems. Over time, components can degrade, connections can loosen, and insulation can deteriorate. Regular inspections can help identify potential problems before they lead to failures or safety hazards. Maintenance tasks such as tightening connections, replacing worn components, and testing insulation resistance can help ensure the continued safe and reliable operation of the system. Additionally, proper documentation of the system is essential. This includes maintaining accurate records of system configuration, equipment ratings, protection settings, and maintenance activities. Such documentation can be invaluable for troubleshooting problems, planning upgrades, and ensuring that the system is operated and maintained safely.